es el título. Es medio
Okay, so let's start with the second talk of today, and it's related to the topic that Alexis was explaining this morning. We gave a tutorial, and now we have a second talk in which Rosa López, who is also a researcher here at IFISC, will explain us more details of other mechanisms in which you interact with these electrons interact in small systems. And basically, she is going to focus on the Condor effect and its use for nanotechnology and nanoscience. Rosa?
Thank you. Thank you. So today I'm going to try to introduce you in the world of many-body physics with kind of paradigm in condensed matter theory, that is the Condor effect. For that, then I will switch between two presentations that I have, because this is a bit technical, this presentation that I did for another school. But I'm going to take advantage of the introduction of this presentation and show you what are the main characteristics of many body effects in nanostructures, like quantum dot or carbon nanotubes, that are reflected mainly on the Condor effect, which is an effect that affects strongly the transport properties of these materials or devices. So, and probably I'm going to repeat the same twice. So correlations in strong correlated systems arise when the electron-electron interaction dominates over the kinetic energy. Then we deal with strong correlated systems, and for instance, we can have high TC superconductors, like cuprate superconductors, or heavy fermion compounds, or even more exotic systems like two-dimensional electron gases that are under the influence of a magnetic field, in a way that you can build kind of fractional quantum Hall effect, where the charge is not, it's fractional. So this effect, the fractional quantum Hall effect, is mainly due to the strong electron-electron interaction in the sample. Also, and I'm going to focus more on this, in quantum dots, I don't know if David has introduced quantum dots. No, not yet. Okay, I will do it. In quantum dots, you can see effect due to the interaction, like Coulomb blockade phenomenon or Condor effect. So the goal is to describe strongly correlated electron physics in which the magnetic moments are the driving force for these strong correlations. So here we have a kind of lattice of atoms. Each of them has an magnetic moment, and the interaction between these magnetic moments among themselves lead you this strong correlated system. And the formation of this magnetic moment is indeed a consequence of the strong interactions or strong electron-electron interaction. So then, for example, in the origin of magnetism in insulator can be found because of the existence of the localized moment, and in metal, the interaction of the localized moment with the metal, in metal with magnetic impurities, for instance, then this interaction between the localized moments and the delocalized electrons in the metal leads to the appearance of the so-called Condor effect. And we are going at the end to focus more on this effect, which is a many-body effect. Okay. So also the local moment formation appears in quantum dot, as I said, giving rise phenomena like the Coulomb blockade and Coulomb. So a big example of correlations is the Kondo effect, and the Bible of the Kondo effect is this book, in which you can learn everything that you want to know about Kondo effect here. All the techniques and the methods to try to understand this phenomenon. I must say that the Kondo effect is a many-body effect. It's a paradigm for Kondo's matrix theory, and it's about interaction between magnetic moments and the localized electrons, and it's a problem that you cannot solve exactly. So for that, then there are many techniques to deal with the Kondo problem, trying to get more and more accurately solution of the problem. So then I think that, well, let us describe maybe the signatures of the Kondo effect. For instance, if you consider a metal with magnetic impurities, then it is known that the resistivity should, at some temperature, when you decrease the temperature, should decrease, because you don't have phonons that increase the resistivity. So then it's expected that in a metal, the resistivity should decrease with temperature. However, quite long ago, in the 30s, there were some experiments in which they showed that for some metal with magnetic impurities, this was not the case. Instead, there was an increasing behavior of the resistivity as long as the temperature was going down. So it was found a resistivity minimum, and the responsible of such a minimum was indeed the correlations in the metal mediated by the magnetic impurities. So it's as I said, it's a many-body effect, and only 30 years after that, after the discovery of this phenomenology in the resistivity of the metals, people could find a solution about what was happening there. So quantum dot in nanostructures. First, as I said just some seconds ago, Kondo effect was discovered in metal, in bulk materials. Later on, it was explained by Jun Kondo, because of that you have the name of the Kondo effect, and almost 60 years after, Kondo effect was observed in artificial nanostructures. So Kondo effect was observed first in bulk materials, and in the, no, more, 70 years. And in the late 90s, then there was the first experiment proving Kondo effect in artificial systems, like in quantum dots, later on in more complex quantum systems, like molecular transistors. For instance, this fullerene attached to ferromagnetic contacts. Then there are many experiments on STM experiments. In STM experiment, you have surface, then you have a tip that can prove the density of individual atoms. So in STM experiments, also people could prove the existence of Kondo effect, because you can attach to the tip a magnetic impurity, and the magnetic impurity is now making a Kondo effect with the delocalized electron of the surface. Also, Kondo effect has been observed in carbon nanotubes, superconductor, it can be affected by the spin orbit effect. You can apply magnetic field, you can drive the system out of equilibrium. So there are unlimited ways to study or investigate this paradigm of the solid state physics in artificial systems. For that, Condorcet has a big success, and it has been investigated from many points of view, and other more complex nanostructures like double dots, triple dots, etc. And now it's also quite a hot topic because it's also related with the Majorana physics, which is Majorana are quasi-particles that have the same amount of electron and hole parts, are very elusive particles, and now people are very excited with the discovery or the proof of the system of Majorana physics. And indeed, also Condorcet embedded in superconductors materials can exhibit a similar behavior as a Majorana particle, which are called SIVA kind of states. Okay, but this is just to let you know that this type of things exist in the literature, and now people are trying to understand better. So, well, first, a general description I'm going to give you about the Condorcet, then the model that people study, indeed, and how Kondo effect arise in perturbation theory. And then I will switch to the other presentation that is more softer than this. This is a heavy. Well, indeed, the lecture is about more than 100 slides, so I will jump on this point because it's very technical. So, a model to describe Kondo effect in methods is by means of by means of two kind of canonical models, that is the Anderson model and the Kondo model. The Anderson model is more complex and can describe a large variety of regimes. Here, as we said, we have a metal, and then we put magnetic impurities in there. So then we need to describe in second quantization language the metal here, okay? So this is the dispersion relation for the metal, and then we have the creation and annihilation operators that create electrons in the metal. Then we have our impurity, and our impurity is indeed a localized level. So the localized level is composed by two contributions: the kinetic energy of the level, which is now represented by this D operator. D is the operator for the localized electrons in the impurity, and the interaction, which is responsible of the system of the Kondo effect. These interactions is so-called Hubbard type of interaction or on-site interaction, and it's an interaction that electron feels when the impurity is double occupied. When you have more than one electrons in the impurity, then you feel this interaction. So it's a kind of on-site interaction. Then you need a mechanism to jump electron from the metal to the impurity and the other way around. So then you need a tunneling coupling between the metal and the impurity. We will see later, in a few minutes, how this model, simple model, can describe also the physics of quantum dots. And I will tell you what is a quantum dot. Okay. So the goal is to try to solve this model. Looks simple, but it's not. Because of the interaction that appeared. Then, when we couple the impurity to the metal, we can have two types of processes because of the tunneling between the metal and the impurity. One process is, you can imagine these K and Q vectors, wave vectors of electrons in the metal, and this is this F is trying to represent the localized impurity. First, you need to have some magnetic moment, so spin up, for instance, for the magnetic impurity, and then you have processes, tunneling processes, that at the end flip the impurity spin by exchanging electrons between the impurity and the metal. So you can have this type of spin flip process in which the intermediate state has no occupation for the impurity, or you can have this other type of processes in which the intermediate state of the impurity is double occupied. Of course, if you occupy with 2 electrons the level of the impurity, then you need to pay this electron-electron interaction, and then this state is a virtual state. So then you can flip the spin of the impurity by means of tunneling processes through this type of virtual states in which you can occupy with 2 electrons the impurity. This is the main essence of the condensate. In this way, by doing this many times, and by doing this having a high order tunneling processes, having this many times, then you are able to flip many times the impurity spin up and down, in a way that many of the electrons that are in the metal are involved, and the final result is that you get a singlet state, which means that no spin, a singlet state between the impurity and the delocalized electrons in the metal. Okay. So this is a many-body state, and this is indeed many-body physics there. So you need many electrons here in the metal that are participating in trying to screen the impurity spin. The resulting state is a singlet state, and what is more important is that the coherent length of this state is quite long. Could be even of the order, as theory predicts, of the order of microns. So you can imagine a singlet state of the order of microns. So this is what theory predicts, but so far experiment has not demonstrated. So you have a kind of macroscopic coherent state formed because of the many-body correlations in the system, because you are trying to screen the impurity spin here by the electrons of the metal. This happens only when you decrease the temperature below some threshold, and the threshold is called Kondo temperature. So energetically, these type of processes are favorable, but when you increase the temperature, then about the Kondo temperature, then these type of processes are not energetically good enough. So maybe I spent quite some time explaining the mechanism, but I think it's good to have a picture in mind about how this effect happens. So here is the mathematics. So you can write down the second order processes that I mentioned before in the picture, in which you flip the impurity spin by having an intermediate state that is empty or occupied by 2 electrons. Then collecting the 2 contributions, then you can write down a effective Hamiltonian that now has a number here, which is the coupling constant at the end, and something there, okay, that depends on the creation and annihilation operators of the impurity and the electrons in the metal. You can write this in this way, and you can realize immediately that this D down D up is indeed the spin operator in which you decrease 1 quantum of the angular momentum here by this S minus, and this is kind of a spin operator for the electrons in the metal. So, but when you rise 1 quantum of angular momentum, 1 quantum of angular momentum. So here you have an effective Hamiltonian that tells you about the spin-free processes. So you have, when you increase the spin of the impurity, then the density of the localized electrons should decrease the spin in 1. So at the end, you can start with the Hamiltonian, that is the Anderson Hamiltonian. You can write down the effective Hamiltonian in terms of spin-free processes, and this is what is called the Kondo Hamiltonian. More specifically, you can have this type of Hamiltonian that is called Kondo Hamiltonian, in which you have some exchange couplings and the scattering couplings. Well, this is just a detail, and this is just telling you that you can also couple your impurity spin with the metal, with the electrons in the metal without a spin. But the important thing is this part that tells you about the spin-free processes. Then you can write in a more illustrative way the Kondo Hamiltonian like this: the metal and the antiferromagnetic interaction, because you are building a spin singlet state. The antiferromagnetic interaction in this way. This is the Kondo model. Now you can do perturbation theory, and this is what the people did in the 60s, trying to understand what was happening in a metal containing magnetic impurities. Okay. You have the Kondo model. Well, you can do perturbation theory in both, in the Anderson model in this way, or in the Kondo model. This was what indeed it was performed. In the Kondo model, you can have your metal and the spin-free processes, and at the end, if you make a lot of calculations, including this type of processes, as I said before, spin-free processes, then you get a second order in the exchange coupling, this term, that is constant, okay, independent of the temperature. But what is important is that in the next order, a third order, in the exchange coupling, then you get a resistivity that diverges with temperature. And this is indeed what you were looking for. Remember that, as I said before, that in a metal, it's supposed that when you decrease temperature, then the resistivity should decrease. But here, you obtain different results. You obtain a result in which, when you decrease temperature, the resistivity increases. So this explains satisfactorily the manifold effect that is responsible of this increasing resistivity with temperature. Another thing that tells you the result is that your perturbation theory fails. dramatically because you have a divergency in your theory. So this tells you that you need non-perturbative techniques to deal with condorcet. And because of that, then the condorcet is really a difficult problem because you need very sophisticated techniques to deal with this non-perturbative technique. So perturbation theory doesn't work. Okay, so then the final result for the resistivity, after doing some renormalization of this divergency, summing many diagrams, etc., then you get nice expression, okay? This way that explains condorcet. Okay. Okay. So then I think that now I can switch, because you know more or less the essence of this variable effect, that you can find in many different condensed matter systems, as I said before. Now we switch to tutorial, okay, and then is view. Because I use very few times Keynote, and I don't remember where now. Ah, it's okay. Thank you. Okay, so I have to go backwards. Okay, so let us start again. So you know what is condorcet about? Now we are going to look at this effect, but in artificial systems. So in nanostructures, for instance, what is called also the two-impulse condor problem, which is again a canonical problem in magnetism. And the role, if we have enough time, of ferromagnetism with condorcet, and some of the work that we have developed here about condorcet in quantum dots, more complex condorcet like the so-called SU4 condorcet, orbital condorcet, etc. So we have introduced the concept of correlated systems, saying that it's because of the on-site interaction. Indeed, it's a good exercise to take a dimmer to sites here with the same energy level, and in which you have some interactions, on-site interaction between them. Okay. Then you can diagonalize the system, and then you can look at the different phases. And depending on the parameters, the interdot, this T is the interdot or intersite tunneling, coupling, and U, then you can see that there are processes in which the two spins of the two sides try to anti-align, because there is a kind of effective exchange interaction between the spin of the two sides. This is the minimal problem that is a precursor of condorcet, let's say. Now you substitute one of the impurities by a sea of electrons that is a metal. So with just this easy exercise of having two sides with interaction and tunneling, then you can obtain the phase diagram, and then you can see that effectively there is a range of parameters when U is very large, in which the two spins wants to be anti-aligned. So there is a kind of effective antiferromagnetic interaction. Now, instead of having two sides, then you can do the same thing with a continuum, and then things start to be more and more complicated, and then you end up with the Anderson model, in which we said before that in an effective way is described by the Kondo model, where you have the spin field processes. Okay. So now let us go to the nanostructure work, in which you can try to engineer a system in which Kondo effect can arise. This is a quantum dot. It's a localized system that contains electrons with some spin, net spin, and is coupled to delocalized electrons. So how to build this? You can take a nanostructure, and by means of the processes that maybe David has explained before, etching and confining, then you can get for instance, like this. You can get one-dimensional systems like this, right? This is quantum nanowires. By etching in a substrate, you can have a series of semiconductor material you can cut. You can get a one-dimensional system, or you can even get zero-dimensional system. You can get zero-dimensional system. In which your electrons now live in like in an atom. So they live in discrete levels. Okay, your electrons. But now, depending on how you build the nanostructure, then the filling of these levels in your 0D system then is something trivial, like up, down, or something more complicated. This depends on how you build this. You can build this even like a rectangle, like probably David has shown some pictures, like a cylinder, or you can build this zero-dimensional system by just having a two-dimensional electron gas and confinement with gates. In that way, then you get what is called lateral quantum dot. So then, in this picture, I can have easily a localized magnetic moment, because if I have an odd number of electrons, then I can have a magnetic moment here. This is my magnetic beauty. So I have a zero-dimensional system that I build in my lab. And now, what I can do is to take this and to couple to some reservoirs of electrons that drives electrical current through it. Okay. I can put here a battery. I can attach here, can put some kind of barrier, some kind of insulating material here also, and then I can put here, can connect this to a reservoir. That can be a two-dimensional electron gas, for instance. You can connect this reservoir and reservoir. In this way, I get my quantum dot. So it's something that is like a quantum well, if you wish, but zero-dimensional. In a quantum well, you have this kind of geometry, but then electrons are free in the two spatial dimensions that are not confined. So, how I can characterize my quantum dot in a simple way? Well, I can say that the only part that I need is my level, the dot level, this in which I have an ampere electron, which is up or down. So I can characterize the level of the dot by just simple with just one level, epsilon naught. Then I have some probability to enter in the dot or to leave the dot. So I can do in the left or in the right side, and then I can assign some tunneling rate, gamma L or gamma R, to constants to the transparency of these barriers. And then I have my method. Okay. So the first thing that happens is, as I said before, now electron fields electrostatic interactions when you try to put charge into the dot. So then the first thing that happens at moderate temperatures means of the order of 1 Kelvin, something like that, is that I try to put one electron on the dot, which is filled with another electron, and then there is no energy, enough energy, to overcome the repulsion, the electronic repulsion between the two electrons. So then what happens is that I cannot do this. Okay. So transport is blockaded unless I have this energy. Then the only way is just, okay, I can do the following. I can just try to, by a gate, I have a gate. Here I push down this level, and then I push down to some value of the energy in a way that the electrons that come there they have enough energy to overcome the electrostatic interaction between the electron that is down and the electron that is coming. Then you measure how is the electrical current versus the position of this level. You have two peaks. One peak is when there's, imagine that this is not filled with no electrons, so then electrons can pass when this level is aligned with this. Okay, so then you have a peak in your conductance. It's not really current, it's conductance, which is the current when the voltage that you apply is very, very small. But you can imagine that these two peaks tell you about when the number of electrons change in the dot. When change? Well, I don't have electrons, then this is aligned with this, and then charge can flow, so I have one peak. And the other peak is allowed when you just move this down, and then the repulsion between the electrons in the dot is overcome. Then you have another peak. So this peak changes electron from 0 to 1, and this peak changes electron from 1 to 2. This is Coulomb blockade phenomenon, in which the transport of charges is blockaded just by an amount of U, which is the on-site interaction. And since it's blockade, people call this Coulomb blockade. Now, what happens if I decrease the temperature? Then something happens, and is that I can have this double virtual state, double occupied virtual states. If I decrease the temperature, then Kondo theta rise, because I have the same physics. I have an impurity spin, magnetic spin, that is coupled to delocalized electrons. And there is an on-site interaction. So strong interactions correlate motion, Kondo effect. Now I can try to flip the spin of the impurity by having this kind of virtual states. They are not energetically variable, but I can have them because it's a virtual state. Since I can have this type of processes in which I'm flipping all the time the spin of the dot, having transport, because at the end you flip the dot, spin, and you pass one electron from left to right. Imagine that you are applying a very small little bias to favor the transport to one of the directions. You transport from here to here electrons, you flip the spin, you are screening the spin of the dot, and then in the region in which the transport was located, now there is transport. This is the magic of the Condorcet, let's say. In a place where before it was impossible to transport electrons from one side to another side of the nanostructure, now you get the unitary limit of the transport, which means the unitary limit is when the conductance gets its maximum value for one channel, which is 2e squared over h. If you think about resistances, then you get the quantum of resistance, the inverse of the quantum of resistance. So transport is completely perfect. This side and this side are perfectly connected, transparent, because of a many-body state. And then at the end you get a Kondo state, which is a singlet state between the electrons that are here and the dot electrons. Okay. So important. Then the linear conductance, your dot is completely perfect. Reach the maximum value. It's also very remarkable that when you are able to compute by some techniques of ring functions, for instance, when you are able to compute which are the effective levels in your dot, then you get your level, epsilon naught, and the level at epsilon naught plus u. Okay. This is what happened in Coulomb blockade. Indeed, if you plot the density of states then of your dot, then you get two peaks that are responsible of the two peaks in the linear conductance. But now you decrease temperature, and then your computer will give you not only these two peaks, but also a peak, very narrow peak, at the Fermi energy. This is the signature of the Condorcet, because now at the Fermi energy, your dot is completely transparent for transport. This is the responsible of having this unitary limit in the conductance. So you get this narrow peak, which has a width of tk, and tk depends on the parameters of your artificial nanostructures, which means that depends on the transparency of this barrier, the position of this dot level, the interaction. So it's something that you can tune in an experiment. And you can go from Kondo regime to non-Kondo regime by tuning the parameters of your nanostructure, your artificial nanostructure, in a way to see Condorcet or not. Because you can have a Kondo temperature that is above the temperature of your experiment or below, depending on how you design your system. This was, as I anticipated before, this was observed in experiments. This is one of the experiments. This is one of the experiments by a group in the Netherlands, in which what they measured was what is called the nonlinear conductance, or the DIDB, or what is the same, the derivative of the current versus the voltage. The density of a state, I can tell you, of something like this, is indeed, you can measure this density of a state in a lab, more or less. You can measure the density of a state for your system by measuring the current and then making the derivative. Somehow the density of a state of your nanostructure is mimicked by the differential conductor or the DID. So here I told you that this is the condo peak, or this is the narrow peak that allow to have perfect transport. Now this condo peak is reflected in experiments like a peak at the Fermi energy or a voltage equal to 0. So this peak with a condo temperature that is the width of the peak is the proof of the existence of condo effect in quantum dots. Later on there have been many experiments, and in this, for instance, this is an experiment already 14 years ago, in 2000, in which they can see how they were able to see this. They were able to see that when you decrease the temperature, condo effect starts, and the conductance grows here. But this is only when you have condo effect. So here, they were able to see the same. They were able to see that when the dot is occupied by an odd number of electrons, okay, you need an odd number of electrons, then you decrease temperature, the conductance increases. When you have an even number of electrons, your dot is not a magnetic impurity because there is no net spin there. So then the conductance, when you decrease temperature, just decrease. So no condo effect. So condo effect only when you have magnetic dots. Let's see. What about the numerical techniques that people used to use? Here, there is a choice, let's say. If you want to describe your problem at equilibrium, no driven voltages, no, for instance, AC potential in your system, nothing that drives your system out of equilibrium, then the best numerical technique is the so-called numerical renormalization group, technique developed by Wilson. But it's only valid at equilibrium. And I say that it's the best because at the end it's a clever diagonalization of the discretized model of the Anderson model, which means that is in numerical renormalization group, what you do is just you have your continuum and your magnetic side. So then you have your magnetic side and your continuum. Now you convert this in a discrete chain. Okay, but many sides that are coupled to this. So then the essence of energy is just to diagonalize this minimal problem. You obtain the states, then you take this state, you use them to diagonalize 3, you get diagonalization, you get the states, you use these states to diagonalize this, and so on. And then until you get some convergence. This is a quite exact method, which is based on a clever diagonalization because there are many details involved in there, but it's very expensive numerically. And to build a good and efficient numerical normalization group code is hard task. Then you have to choose either I want a good approach for equilibrium problems or approaches for deal with non-equilibrium transport. For instance, transport when you take your dot and then you apply a battery here, so some differential potential between left and right chemical potential. Then you need to use different techniques that incorporate the fact that you are out of equilibrium. And then you can use diagrammatic techniques in the framework of the so-called Keldysh technique. For green functions, you can use sophisticated way to describe this, like a slave boson mean field theory, or diagrammatic using this slave boson representation. Or you can use also the technique of equation of motion, etc. So there is plenty of numerical ways to deal with quantum effect using indeed quantum field theory, because this is quantum field theory, using green functions, diagrammatic techniques, or equation of motion. It's a technique that has been improved during these last years for this problem. I'm almost finishing, so I think that at the end I just told you half of that I want to tell you, but I think it's enough. If you at least have captured the essence of quantum effect, which is canonical problem in many of the complex matter systems. So I want to emphasize now then that in the quantum effect in nanostructures, it's important to say that the dot level is renormalized at the Fermi energy. As I said, there is a new peak at the Fermi energy. The width is given by quantum temperature that can be tuned by the external parameters of your sample. And the way to measure this is by the DIDV, which is the derivative of the current versus the voltage. And then I should maybe stop here, because then a new topic starts, that is the quantum effect in double dot, in which now you can think about more complex systems in which you can combine the quantum effect here and the quantum effect there. You can have hybridization of quantum effect, quantum clouds here and there. You can study the different phases of this system. And this is also an artificial system. Instead of building this, you can have two dots coupled by means of a tunneling barrier and then coupled to reservoirs. You can also imagine that these two guys here, they have some antiferromagnetic interaction. So there is a competition between the antiferromagnetic interaction between the two localized spins and the antiferromagnetic interaction due to quantum physics. Then you can have plenty of phases here that many of them have been already proved in experiments. So I think that I should stop here, and thank you very much. Well, if you have some questions, or I will be very pleased to answer. Maybe it's new topic, new things.
Questions?
Thank you.